Greetings. The title of my project is A Novel Approach to Citrus Disease Management, leveraging computer vision, machine learning, and convolutional neural networks. My project ID is SIMRS018.
Huanglongbing, or HLB, is an incurable disease that affects citrus trees. It is also known as citrus greening. HLB is caused by the bacterium Candidatus Liberibacter asiaticus and spread through the Asian citrus suet, which is a gnat-sized insect. The disease originated in China, but it eventually spread to Florida in 2005. The disease makes citrus leaves become yellow and shriveled, and it makes citrus fruits become lopsided and bitter, and therefore inedible. In the U.S., HLB has caused about a 21% decline in the fresh citrus fruit market and about a 72% decline in the production of oranges used for juice and other products. Citrus production in Florida alone has decreased by 74%, and the number of citrus growers in Florida decreased from 7,389 in 2002 to 2,775 in 2017. The treatment of HLB is handled in a two-step process, starting with identifying infected citrus plants and controlling the disease. So far, there are no commercially viable techniques to cure HLB, only laboratory-based methods. Because of this, farmers spend lots of time and resources in manually identifying HLB and removing infected plants to control it. The main focus of my project was to develop a semi-autonomous system that identifies whether a plant is infected with HLB using a neural network-based artificial intelligence model trained with labeled images, a Raspberry Pi mini computer platform, a webcam, and a GPS receiver on a remotely piloted aerial system, and a prediction software programmed in Python on the Raspberry Pi with the trained model and the physical components of the system. A neural network works similarly to a human brain's neural network. A neuron in a neural network is a mathematical function that collects and classifies information according to a specific input. Neural networks are utilized in several fields for data analysis, interpretation, and inferencing. A neural network always consists of an input layer, at least one hidden layer, and an output layer, as illustrated in this image. The layers are interconnected through nodes, also known as neurons, with each hidden layer using the output of the previous layer as its input. Convolutional neural networks, or CNNs, are a special kind of neural network that are meant to be used for recognizing and classifying images and videos. In a typical CNN model, there are two types of hidden layers: feature detection layers and classification layers. The feature detection layer is composed of convolution, pooling, and rectified linear unit layers. The convolution layer puts images through filters, activating certain features that become important in the overall model. The pooling layer simplifies the output by reducing the number of parameters that the network needs to learn about. The rectified linear unit layer allows for faster and more effective training by optimizing values. These three operations are repeated multiple times within each layer to learn and detect different features. The output from the feature detection layer is then fed to the classification layer. The first layer of the classification layer is called the flattened layer, which converts an input to a single long feature vector. A vector is basically a list of data points. The fully connected layer, or dense layer, outputs a vector with a dimension equal to the number of classifications that the network is trained to predict. The final layer is called the softmax layer, where the model utilizes a special softmax function to convert the outputs from fully connected layer to probabilities to categorize an image. The detailed engineering goal of this project was to 1. Define, develop, and train a deep learning CNN model using sample images of leaves infected with HLB and those that are not infected with HLB. 2. Assemble a mini computer platform such as a Raspberry Pi to develop the detection system integrated with the webcam and global positioning receiver, onboarded on a remotely piloted aerial system for real-time prediction and detection of citrus plants infected with HLB. And 3. Develop a prediction software using Python that leverages the trained model to predict whether citrus leaves in a new and unseen image are infected with HLB and to locate the exact spatial coordinates of infected citrus plants using a GPS module. This slide shows all the major components of my project as described in the engineering goal. The main steps of my project are shown in this slide. After gathering materials, the environment to develop the software was set up. Next, images of healthy and HLB-infected citrus leaves were collected from several local citrus growers and nurseries to train the CNN model. The CNN model was then defined and trained using Jupyter Notebook and Python. The system consisting of the Raspberry Pi, the GPS receiver, and the webcam was then assembled. After assembling the system, the prediction software that utilizes all these parts was developed in Python to apply these components and the trained CNN model in real time. Finally, tests were run to test the system and the model's success. This is an outline of the CNN model that was defined and trained in this project for citrus disease identification. It consists of 8 layers for feature detection, utilizing all 3 types of layers, namely convolution, pooling, and rectified linear unit, and 3 layers for classification, namely flatten, fully connected, and softmax. This slide shows snippets of the program created to define, develop, and train the CNN model for citrus disease classification. This slide shows snippets of the prediction software developed in Python utilizing the webcam and GPS receiver as well as the trained CNN model to identify HLB-infected citrus leaves in real time. Both of these full programs are included in the supplemental documents of my presentation. Here is an image of my assembled system. Number 1 is the Raspberry Pi mini computer platform, where the citrus disease detection software is executed from. Number 2 is the battery pack to power the Raspberry Pi. Number 3 is the Canon webcam that captures images in real time to classify. Number 4 is the GPS receiver that is responsible for obtaining the exact spatial coordinates of the infected citrus plants. Here is the system from the previous slide mounted onto a working remotely piloted drone, allowing the system to fly around citrus groves to identify HLB on citrus plants in real time. The performance of a CNN model is evaluated by comparing the loss and accuracy metrics of the training set and the validation set. A loss function is used to optimize a machine learning algorithm. The loss is calculated on the training and validation datasets and interprets how well the model is doing in each of these 2 sets. The loss is the sum of errors made for each example in each set. Loss value indicates how poorly or how well a model behaves after each iteration of optimization. An accuracy metric is used to measure the algorithm's performance by comparing prediction with the actual label. The accuracy determined for the training set and the validation set is calculated in percentage and represents the ratio of examples predicted correctly matching the actual label in the set. As seen in the 2 graphs, the loss and accuracy metrics for the training set and the validation set show a similar and converging pattern respectively as the model's training progresses, and it can be stated that the model developed and trained in this project is a well-performing model. The tables depicted here are sample sets of the results of the system's real-time classification of images of citrus plants with HLB and healthy citrus plants. The full results for both of these datasets can be found in my research plan. The results from the experimentation demonstrate that the engineering goal was achieved. The experiment demonstrated that as citrus plants or citrus leaves were placed in front of the HLB detection system, the system was able to identify accurately 90% of the time whether the plants were infected with Huanglongbing or if the plants were healthy. This approach can be extended to identify additional citrus diseases such as canker, black spot, and melanosis in the future. Furthermore, the method and system can be applied to disease management for other crops as well. Here is a video of the citrus disease detection system in action. Thank you for the opportunity to present my STEM Fair project. If you have any questions, please feel free to contact me.